This demonstration is going to cover what's known as two-beam imaging. So the first thing to clarify is that whenever discussing two-beam imaging is always done within the context of usually a single crystal specimen or a single crystal region within a specimen. The specimen that we have today is a single crystal of silicon that has been ion implanted and subsequently annealed, and as a result has small faulted dislocation loops in it, which provides basically an ideal specimen to test out and demonstrate two-beam imaging. The other thing to keep in mind is that whenever you're doing two-beam imaging, you must use a double tilt holder. So the double tilt holder is already loaded inside of the column here. You can always tell if a holder is double tilt because it has this extra cable coming off of the back of it that's used to control the beta tilt. So the two tilt axes of the holder, if you look here at the holder, there's the long axis that runs into the column here. Okay, so I can tilt the holder like this, about this long axis of the holder. That's called the alpha tilt on this particular instrument. So the other tilt axis is perpendicular to the long axis and actually goes like this, and that is known as the beta tilt. So we need both of those tilt axes if we're going to perform effective two-beam imaging. It can't be done with a single tilt specimen or a single tilt holder. Okay, so before getting started, just like you're doing normal TEM imaging, you have to perform your basic alignment. So we have spot size 1 selected, which is typically what's used when doing two-beam imaging, and when doing specifically weak beam dark field imaging, that's always the spot size you should use. You want to set the sample at eucentric height, center your C2 aperture, correct your condenser astigmatism, perform rotation centering, just as you would normally. So from here, what we're going to do now is actually set up the two-beam condition. So to set up the two-beam condition, we need to go into diffraction mode. And if we look on the screen there, we can see the diffraction pattern. So this is a 001 oriented silicon sample, and as you can see, we're actually pretty close to a two-beam condition. Again, a two-beam condition would be one where I have the direct beam and one Bragg beam basically dominant in the diffraction pattern. But what I'm going to do instead is I'm going to tilt the sample to align it basically perfectly with the 001 zone axis, and I'm going to start from there and then reestablish the two-beam condition. So over here, on my left-hand panel, I have my alpha tilt and my beta tilt. Whenever you're adjusting these, you always want to start with the alpha because the alpha is eucentric. Get it as close as you can, and then you want to move to the beta tilt. Okay, so I'm just going to start with the alpha tilt here. Okay, you can watch the diffraction pattern here as I adjust alpha. Okay, be a little. Okay, so you can see I can't quite get it with just the alpha tilt, so I'm going to go to the beta tilt now. Alright, that's getting worse. Right. And so now I'm basically aligned with the zone axis. You'll also notice that the spots got a lot fainter. What that usually means is that you're not on the same area of the sample, and you're probably on an area that was a little bit thinner than when you started. So when you're adjusting the tilt axes like this, it's not uncommon for your area of interest to move from under the beam from where it was initially. So what I'm going to have to do now, go back into image mode. Okay, and you can actually see, it's probably a little hard to see, but I'm right at the edge of the sample. Okay, so I have a lot of open space in there that's contributing to the DP, which explains why I lost a lot of that signal. Okay, so I'm just going to move the stage back right here. So now I'm basically over everything, over sample. Okay, I go back into diffraction. Okay, and so you can see now I have my diffraction pattern aligned with the zone, or the specimen aligned with the zone axis. Okay, so I turned off the lights, and hopefully that's a little more distinct. Okay, so hopefully you can see that, but I have 4 distinct Kikuchi bands. Okay, they're all running straight through the direct spot. Okay, so I have two Kikuchi bands that correspond to 220 family of reflections. The other two correspond to 004 family of reflections. But right now we're on axis, and this obviously isn't a two-beam condition. So what I'm going to do now that I actually have the sample aligned with the zone axis, is I'm going to tilt off the zone axis to establish a two-beam condition. And I'm going to, for the purposes of this demonstration, establish a 220 two-beam condition. So again, I'm going to come over here, use my tilts. I'm just going to start with the alpha again because alpha is eucentric. Alright, so that's really closer to one of those 400 families. And what I'm probably going to have to do here is stop right there. I'm going to go to the beta tilt now. Alright, so right about there. Okay, and this is probably a little tricky to see, but I have my Kikuchi lines. Okay, so I have the Kikuchi line on the right. There's a Kikuchi line that's running straight through the Bragg spot. The one on the left is running straight through the direct spot. Okay, so this is actually what's known as a deviation of 0, meaning I'm exactly at the Bragg condition for the spot, okay, which is where we're going to start, and we're actually going to see the effect of this on the subsequent image. One thing you have to be cognizant of whenever you do a lot of tilting of the specimen is that in doing so, you usually end up deviating slightly from eucentric height. So since we did some tilting of the sample to set up the two-beam condition, I'm actually going to now re-establish eucentric height. So just like in the previous demo, okay, press eucentric focus. Okay. And so again, we're going to adjust Z to minimize the contrast. We're not off by a whole lot. Okay, so that's getting worse. And right about there, if I keep going, I see the contrast again. Right about there. Okay. And now to complicate matters, ideally my two-beam condition shouldn't be any different, but I'm going to go back into diffraction mode anyway here. Okay, and actually it looks basically the same. Sometimes if you do a large move with the Z, if you do a lot of tilting, for example, when you go back and look at the two-beam condition, it might not be quite where you initially thought it was, but it seems that we have preserved it because we didn't do that much of a move with the Z control. So we have the two-beam condition set up, and for our purposes we'll call that the 220 two-beam condition, and again that's with the deviation parameter of 0, meaning we're basically exactly at Bragg condition. So now if I inserted an objective aperture small enough to only select the direct beam, or a single beam if you will, and I positioned it around the direct beam, that would form a bright field image. If I wanted to form what's known as a centered dark field image, I have to tilt the beam. And so I actually do that in a manner that will result in the direct beam moving to the position of the Bragg beam, which again, the Bragg beam is the beam on the right, direct beam is the beam on the left. So in order to accomplish that, I come over here to the right-hand panel, I hit the dark field button. What that does now is it activates the multifunction knobs on both panels as beam tilts. Okay, so you can see now, see if the camera will focus there. And you can see now I'm moving, okay, I'm moving that direct spot from where it was to where the Bragg spot is, okay? So now I have the spot that was opposite the Bragg spot, which we call minus G. Okay, now I have that spot bright in place of the, instead of the original Bragg spot, which again is on the right of the direct beam, you can see is now dimmer. Okay, so now the minus G Bragg beam is now along the optic axis. So if we select that beam with the objective aperture, we would form a centered dark field image, or sometimes known as an axial dark field image. Okay. The nice thing about the system is, if I come back here, I can switch between the two configurations just by hitting this button. Okay, so by turning that off, okay, I go back to my initial 2-beam condition where I didn't have the beam tilted at all. Okay, so what I'm going to do now is I'm going to insert an objective aperture, and I'm going to center it around the direct beam. And for our purposes, when you're doing this, you usually want to use the smallest objective aperture that you have. So if I come up here to my objective aperture strip, okay, so again, 4 through 1 are actual apertures. 4 is the smallest, and 4 is the one that we use whenever we're doing bright field or general 2-beam imaging, because we can only select or want to select a single beam. Okay. So this is a little tricky to do here, so I'm going to do this using the binoculars and the focusing screen, because that's usually the most accurate method to do it. Okay, so I've inserted objective aperture 4, and you're seeing the image of it right now on the focusing screen, and clearly I don't have that around the direct beam, so I'm adjusting my aperture shifting knobs I should say, until I'm centered around the direct beam. And again, I'm going to fine-tune this by looking through those binoculars, but just to kind of demonstrate what this looks like right here. Okay, so assuming I have that centered perfectly, what I'm going to do now is come back to the dark field button here, and now I have my configuration set up for the center dark field, except now I have -G at the location of the direct beam. Okay, and so what you typically do now as a result of this, because now I've hit the dark field button and my multifunction knobs are now activated for beam tilt, is I would actually look through the binoculars and adjust multifunction knobs until I get the -G brag spot at the exact same position of the direct spot. So I'm going to go ahead and do this, and then I will turn off the dark field button, so we're back starting with the bright field condition. Okay, so I have the dark field button off, and my objective aperture centered around the direct beam and only selecting the direct beam. So I have the condition for bright field image. So I'm going to go back here and go into image mode. Okay, so you can see the bright field image now on the screen, and I'm going to resize my area of illumination with the intensity knob, so I'm a little bit bigger than that 40mm circle. And before we insert the camera, one thing that should be mentioned is that you generally don't need a very high indicated magnification when you are doing 2-beam imaging. You are operating under conditions such that your resolution is usually in the nanometer range to begin with, so you don't really gain a lot of benefit from using a very high indicated magnification. On this particular instrument, we typically don't go much higher than this indicated magnification you're seeing here. We will go a little bit higher, but not much. At some point it basically becomes diminishing returns. So now I'm going to come back into microscope control, go to the camera tab, and hit search to insert the camera. Alright, camera's inserted, so now I just need to lift up the viewing screen. So I hit the R1 button here. Okay, and there's my bright field image. Okay, so I'm going to go ahead, I'm going to increase my exposure time here, give me better signal to noise. Okay, so you can see a few different features here in the bright field image. So the little dots are the faulted dislocation loops. And actually, I'm going to go up in magnification just one setting here because it's going to make this a little bit easier to do. So again, if we want to do that, come back here, put the viewing screen down. I went up to indicated 17,000x. Okay, resize the beam so we're a little bit bigger. Alright, so it's a little bit easier to see those now. Okay, so you can see those dots, those are the faulted dislocation loops. Focusing in bright field can be a little bit tricky. So again, I'm using the focus knob here. And usually the best way to do this, since you have the faults there to look at, you want to get those as sharp as you can get them. We don't have an edge in this particular portion of the sample. If we had an edge, we could focus on that. But that's about as good as we can get right here. So one thing you'll notice here, again, I have a deviation parameter of 0. Okay, my faults are not very distinct when I do this. Okay, because I have a large contribution from the regions of the specimen that are non-defective. Okay, so we're going to talk about in a minute how to alter the two-beam condition to change that. But before we do that, we come back here to the right-hand panel. Okay, if I hit the dark field button, okay, I now have the center dark field image. So I'm going to leave the camera here. Okay, bright field, center dark field. Okay, so I have a contrast reversal when I do this. Right, what's bright in the dark field becomes dark in the bright field. I'm sorry, let me repeat that. What's bright in the bright field becomes dark in the dark field, and vice versa. Okay, so the CDF image really isn't any more beneficial in terms of the contrast that I get. I don't have what's known as sharp contrast, meaning it's hard to delineate the faulted regions from the non-defective region of the material. Okay, and just really quickly here, if we want to do an acquire just to see how these look, I'm going to use a second here. Okay, so that's the bright field image, again with S equals 0. So you can see these faulted dislocation loops. Okay, now I have the CDF image. Okay, and that's the CDF image. Okay, and so now we're going to talk about how to change our imaging conditions to get us some sharper contrast. Okay, so I'm back in diffraction mode. I have the dark field button off, so my beam isn't tilted. Okay, so again, I have a deviation parameter of 0 here. My Kikuchi bands are running straight through the direct spot and the Bragg spot. If I tilt the sample such that it pushes the Kikuchi bands to the right of both of those spots, okay, so the band running through the direct spot will move a little bit to the right of the direct spot. The band running through the Bragg spot will move a little bit to the right. Okay, I end up with a positive deviation parameter. Okay, so I'm going to start here. I'm not sure which way I'm going to have to tilt. I'm going to start here just gently touching. I don't have to do a lot of tilting for this usually. Alright, so there you go. You can see now, it's probably a little hard to see, okay, but my Bragg beam isn't quite as bright as it was. Okay, so again, if I'm deviated from the Bragg condition, meaning my S is now positive, I wouldn't expect my Bragg beam necessarily to be quite as bright. Okay, but I have an S that's positive now. Okay, so I didn't adjust the beam tilt, but if I hit the dark field button and I come over here, okay, I have the same thing now, but I have this set up for a CDF image. Okay, so I hit the dark field button again. Okay, so just like what we did before, I'm going to insert my objective aperture, center it on my direct beam, okay, and then I'm going to switch to dark field mode, and I'm going to adjust my multifunction knobs so my -G beam is where the direct beam is in bright field mode. Okay, so I'm going to go ahead and do that really quick here, and then we'll look at the difference in the images. Okay, so we're looking at the bright field image right now. So I'm going to go ahead and flip up the viewing screen here, take a look at what we have. Alright, so I now have an S that's positive. Okay, so one of the things you'll notice hopefully immediately is it's easier to pick those faults out from the background. Okay, so by going to an S that's positive, I get less of a contribution in the image from the non-defective regions of the specimen, okay, which would basically be everywhere that I don't have faulted dislocation loops. I'm going to go ahead and just focus here really quick, see if I can get it any better. No, not too bad right there. Alright, so I'll go ahead, I'll do an acquire here really quick. Alright, so this is with the bright field with S greater than 0, and that's the same image but with S0. So clearly this provides us with what's known as sharper contrast, in that we can delineate the faulted regions from the background with more clarity. So if I now hit the dark field button, okay, so now I have the CDF image. So the same benefit that we got in bright field by going to positive S, we get in the CDF image, except now my contrast is reversed. Okay, so my defective regions were dark in the bright field image, now they are light in the dark field image. Okay, usually your focus isn't too different between bright field and dark field, but you can always go ahead and just adjust it a little bit when you get into dark field. Yeah, so it's not too much different there. Okay, but you can again see, you can see the big difference there between centered dark field with S 0 and S positive. Okay, all right. So if we pull up, all right, so that's the dark field with S equals 0, and that's S positive. So we can pick out the faults more readily. That being said, the best way to provide the sharpest contrast is not with bright field or centered dark field. It's with what is known as weak beam dark field imaging, and that's what I'm going to show you how to set up next here. Okay, so I have the dark field button off, and I actually tilted the sample to get back to a deviation parameter of 0. So one other thing I'm going to do here really quick, I'm going to re-zero my tilt in the dark field control. So if I hit the dark field button here, okay, if I click on the dark field tab up here in microscope control, okay, there's a reset button, so I'm going to hit that. Okay, that resets my tilt, so now when I have the dark field button activated, my tilt is identical to when I have the dark field button off. Okay, and that's always where you want to start with. Hopefully the person before you did that when he or she was done with his or her session. Okay, so right, so I hit the dark field button and turned it off. So now we're in the bright field mode. Okay, so now if I want to set up what's known as a weak beam dark field image, I have to tilt the beam just like I did in centered dark field, but how I tilt the beam is different. So when you're doing this, you want to start from an S that's basically 0 or slightly positive. So we do have an S of 0 right now. Okay, again, left is the direct beam, right is the Bragg beam. And now what I'm going to do is tilt the incident beam to move the direct spot to the spot that is opposite of the Bragg spot. So in other words, that Bragg spot to the left of the direct spot that is dim right now. Okay, or conversely, if it helps you, you could think of it as I'm moving the Bragg spot to where the direct spot currently is. Okay, so I'm going to come back, hit my dark field button. Okay, and now again my multifunction knobs now control beam tilt. Okay, so I'm tilting the beam here. Okay, and let's see if the camera will get a little bit better focus. All right, that might be a little hard to see because there's only the direct beam basically dominant in the picture, unfortunately. But anyways, that's what I've done here. Okay, I'm going to switch back here. That's bright field mode. See if it'll get a better focus. Yeah, it'll get a better focus here. Okay, so if I do this really quick, okay, unfortunately my camera doesn't really like that. Okay, but again, I've tilted the beam to move the direct spot to the position of the beam that is opposite the Bragg beam. Okay, what has happened as a result of that as well, and this is going to be hard to see, so I'm going to have to describe it here. When I go back into dark field mode, if you look 3 Bragg spots to the left, not the left, sorry, to the right, okay, of my direct beam, you'll actually see that beam looks lit up. Okay, that's exactly what happens when you tilt to set up a weak beam condition. So sometimes this is known as a G3G condition. Okay, so the Bragg beam that was to the right of the direct beam is now along the optic axis, and we're deviated now from the Bragg condition for that spot. Okay, so we expect that to be fairly weak in intensity, which is where we get the name weak beam. Okay, so to proceed from here, okay, I go back into bright field mode. I'm going to center my objective aperture around my direct beam. I'm then going to go back into dark field, and I'm going to finally position the Bragg beam within the objective aperture so that they're both along the optic axis. And then we'll take a look here and see how the images turned out. Okay, so I have the objective aperture on the focusing screen, and I'm in bright field mode right now. It's probably hard to see, but I have the objective aperture centered around the direct beam. If I go into dark field mode, okay, you can actually see, it's probably a little hard, but my Bragg beam, which should be centered, is now a little bit too far to the right. Okay, so this is where you have to use your multifunction knobs here, and now it's basically centered inside the objective aperture, so now it is down the optic axis. Okay, so I'm going to hit the dark field button again to go back to bright field. We will start by looking at this image, and then we will compare it to the weak beam image. Okay, so this is my bright field image, and again we started from S equals 0, and we already saw the contrast that we got as a result of that, which we determined was not very good or sharp. Okay, so now in order to switch to the weak beam image, again I just come back here, hit the dark field button. I'm going to actually show the screen here, and there is the dark field image. Okay, so you'll notice, or the weak beam dark field image, I should specify. Okay, so you'll notice that I lost quite a bit of signal. This is normal when you're doing weak beam because you are using a, by definition, weak beam. Okay, so I'm going to increase my exposure higher than what I would probably normally use. Okay, when I'm doing bright field imaging. Okay, and so now we can actually see that compared to any of the images we've seen before, my faults actually look way more distinct, again, compared to the non-defective background. Your exposure times when you do this, so it's not uncommon to use several seconds here. I'm going to put 6 seconds in. This is going to take a little bit here. Okay, so that's not too bad. There's your weak beam dark field image. So you can see a fairly good amount of detail in those faulted dislocation loops. Again, if we pull up, that's the CDF image. Okay, so compared to the CDF image with positive S, we get sharper contrast with the weak beam. Okay, and that's the bright field with the positive S. Again, we still get sharper contrast here with the weak beam. So this is accepted as usually the best method of getting sharp contrast when you're imaging faults. I'm going to decrease my exposure time here for a second. Okay, one thing I would like to point out is that if you move around on the sample, your sample is most likely not flat and is bent. And if you move from where you've set up your two-beam condition, you will probably find that your two-beam condition is a little bit different from where you were initially. So you can usually move a little bit from where you were initially, but it usually doesn't take long and you don't really need a whole lot of specimen tilt to begin with. Okay, but you can see here this is actually a little bit better area than what we had. Okay, the only point is you probably want to be just a little cautious about doing a large move with the sample, because more than likely your sample isn't flat and you end up with a slightly different two-beam condition than what you initially had, where your S might not be 0 initially, it might be positive or it might be negative. So I'm going to go ahead and do another require here really quick. Yeah, there we go. So it's a nice weak beam image. Okay, so I'm done with my session here. I'm going to do a couple things here. First thing is, I have the dark field button activated on the right hand panel. I go to the dark field tab. I want to reset the tilt back to 0. Okay, I don't want to leave that activated, and then I don't want to leave the dark field button activated either, so I press that to turn it off. Okay, track the camera. There's my column valves. Okay, the same stuff that was covered in general operation of the instrument. I'm going to take out my objective aperture here. Okay, so that's out. And then reset the holder, go to the stage tab, expand the flap out, and then reset the holder. Okay, so we adjusted the tilts this time. So again, here you want to be careful. Again, verify X, Y, Z, alpha, beta are all basically zeroed out, which they are. And so at this point, we can extract the holder and finish the session, which I'm not going to go over. But this concludes the demonstration of the instrument for two-beam imaging.